Good morning to all. Welcome to the online lab session for Wireless and Mobile Communication Lab for the seventh semester with subject code EC71. I am Anush TR from the Department of Electronics and Communication, New Horizon College of Engineering. In this video, we will be considering the second experiment, which is Okumura model. So we will be using the Matlab to implement this. So let us have a basic understanding of what is Okumura model. So Okumura model is one of the most widely used model for signal prediction in urban areas. Okay. This model is applicable for a frequency ranging between 150 megahertz to 1920 megahertz. And the distance, that is the separation distance between the transmitting and receiving antenna, has to be in a range of 1 kilometer to 100 kilometer. And the base station antenna height has to range between 30 meter to 1000 meter. So these are the few condition laid by Okumura when he had, you know, developed his model. That is, the frequency has to necessarily be in this range between 150 megahertz to 1920 megahertz. The distance, the separation distance between the receiving and the transmitting antenna has to be in the range of 1 kilometer to 100 kilometer, and the base station antenna height has to range between 30 meters to 1000 meters. Now, the model is expressed using a formula given by L50, which is the Okumura path loss, is equal to LF. LF is the free space path loss. We'll consider each of these terms. So LF plus A mu F comma D minus the gain with respect to your uh, due to your height of your transmitting antenna minus gain of the gain due to the height of your receiving antenna minus G area. So we will consider each of these terms independently. Now let us see what are these terms. So as I told you, L50 is the 50th percentile value of propagation path loss calculated using the Okumura model. LF is the free space propagation loss. We will also look into the formula of this. AMU is the median attenuation relative to free space. Now this Okumura had generated a curve, by putting few conditions into application, and he developed a curve, and we will be using this particular curve to calculate what is the value for AMU for a given frequency and a given separation of distance separation between the transmitting and receiving antenna. We will look into it. I have taken a consideration of a graph, so we will be seeing how we calculate this. And then coming to the base station antenna gain factor, height gain factor, it is given by 20 log ht by 200. Okay, and the height has to be in the range of 1000 between 30 to 1000 meters. Going further, we have GHRE, which is the receiver gain height gain factor. Okay, receiver antenna height gain factor. Here there are two considerations. One is, if the receiver antenna height is less than 3 meters, we will be using this formula, which is 10 log HRE by 3. Okay. Similarly, if the height of your antenna lies between 3 meter and 10 meter, we will be using the formula 20 log HRE by 3. And G area is the gain due to the type of environment, which again was given as a curve by Okumura. So it is a curve wherein we will be, whatever frequency is being used for that particular frequency, what is the area under consideration, whether it is an urban or a suburban, a quasi open rural. So based on what area, we will be choosing the corresponding gain. So we will look into it next. Now, LF, the free space path loss, it's given by 10 log to the base 10 lambda square by 4 pi square d square. This is the formula we will be using, where lambda we can calculate. We know the speed of light, we know frequency is given to us, so we can calculate lambda. D is the separation distance between your transmitting and receiver antenna. So this is how you can find out the free space path loss. Going further, yes. As we discussed, to calculate AMU, we were given a curve. Now, this is the curve from which we can calculate AMU, okay, which is the median attenuation relative to free space. So how did Okumura develop? Okumura developed a set of curve giving the median attenuation relative to free space AMU in an urban area. So his consideration was urban area, a quasi-smooth terrain. Now he chose some specific standards. That is, he chose the base station effective height at 200 meters and a mobile station antenna height of 3 meter. That is, the receiving antenna height he considered was 3 meter, and the base station transmitting, base station antenna height he considered as 200 meters. So he used a predetermined standard, and using this he had given us these curve. Okay, this is the first curve which is for AMU, and similarly he gave a curve for your gain factor G area. That is, Okumura developed a curve for correction gain factor which accounts for the type of terrain. Now you can see here this curve he gave to find out what will be the value for G area. Okay. Now let us see how exactly we can find this. Now let me consider the frequency under consideration is 1000 megahertz, and the separation distance between the receiving and transmitting antenna is 50 kilometer. In that case, how will I find the value for AMU? Okay. See, the x-axis here indicates the frequency in megahertz. The y-axis, I can see there are two sets of values for the y-axis. One set of the value will give me is corresponding to the separation distance between the transmitting and receiving antenna, and it ranges between 1 kilometer to 100 kilometers, because that is the range prescribed in the Okumura model. And we have an outer y-axis which is giving us the median attenuation, that is the value of AMU, that is in dB. So this will give us the value for AMU. Okay. Now, as I told you, here we are considering a frequency of 1000 megahertz. So let me come here. 1000 megahertz is this point. So I take it up. I see which is the curve corresponding to 50 kilometers, because the separation distance which we have considered here is 50 kilometers. So for 50 kilometers, we see the curve goes here, and this is the point where it's the point where the 1000 megahertz frequency line would meet the curve of your 50 kilometer curve given by Okumura. Now you can see this point. You can take this point, you can extend this line towards the y-axis, find the corresponding point on your y-axis to find what will be the median attenuation in dB. And you find it, it reaches here. So let us say it is between 40 and 50. It is more than half of, the distance between them. So approximately I have taken it as 46. Okay, I hope everybody has understood this. For a given frequency which is under consideration, I considered here it as 1000 megahertz. Okay, just for the purpose of making you understand, I have taken this as 1000 megahertz. It depends upon what is given in the problem which you are supposed to solve. So 1000 megahertz, and the distance of separation between the receiving and transmitting antenna is given as 50 kilometers. So we are going to choose what is first we find where is the frequency corresponding to what is given. So we have been given with 1000 megahertz. So this is the point, and we have to find out the corresponding curve depending on the distance between the receiving and transmitting antenna. So that is 50 kilometers. So this is the curve which we have to consider. So we have to see where the 1000 megahertz and this 50 D50 would meet. This is the point where they would meet. From here, we will extend this point to your y-axis to find what will be the median attenuation. So this will provide us the value for AMU. Okay. So this is how we find the value for AMU. Going further, you can see in this, as we had discussed earlier, the consideration which he had taken is the height of your transmitting antenna is 200 meters and the height of the receiving antenna is 3 meters. Okay. Now, let us go further. And here we are being given with the graph or the curve given by Okumura to calculate G area. Now, here in the x-axis, we have the frequency, and y-axis we have the G area correction factor. Okay, this will be giving us the value for G area correction factor, which can be used in the problem directly. Now let us again consider, a frequency. I have considered 1000 megahertz here. So on the x-axis, let me find out where 1000 megahertz is, and then I have to find from my problem what is the area which is given. Is it a suburban area? If it is suburban area which I have considered here, I would take 1000. I should see where this will meet my curve of your suburban area, and that point has to be chosen, and I have to extend it on towards the y-axis and find where it meets. Now for this particular case, for 1000 megahertz for a suburban area, I found out it meets a G area value of 10 dB. So I have chosen here the G area value as 10. Now instead of, say, let me just for a consideration for your understanding, if I am considering the frequency to be, say, frequency to be, I'm sorry, okay, for our consideration, let us consider the frequency to be 500 megahertz, and we can consider a quasi open area. Okay, quasi open area. So what we'll have to do, we'll have to find this point on the frequency axis. This is a point corresponding to 500, and then we'll have to extend it up. Okay, we'll have to extend it up till it reaches the quasi open area curve, and say it approximately meets at this point. Now from where we will extend further towards the y-axis. So it's approximately 19. See, the way I drew, there might be some, error. That's fine. It's for your understanding. So we got, for this particular case, we got the G area value to be 19 dB. Okay, so this is how we find out the value for G area as well as AMU using your Okumura model. See, the other factors which is involved can be calculated using the mathematical expressions he has given. That is, whether it is to find LF, which is the free space propagation loss, and the GHT and GHRE can all be calculated using the mathematical expression provided by Okumura. Only for calculating AMU and G area, we will have to adopt the method which I thought, using the curve. So everybody should have a thorough understanding on that. And something which is again interesting, which is worth mentioning also, if you have noticed in this model what was provided by Okumura, you can see wherever there is gain, like GHT indicates the gain of your transmitting antenna height. Similarly, GHRE for your receiving antenna height, and G area is pertaining to a given area, what would be the gain. All the gains have been subtracted, and you have LF, which is the path loss for your free space, and AMU F comma D, which is also the attenuation, which is the loss. So all the losses are added and gains are subtracted, because ultimately what we are finding out is the propagation path loss using Okumura model. So it is the loss which we are calculating. So we are adding all the losses and we are subtracting the gain from it. That's why all the gains are being subtracted for this particular model. Okay. Now let us go further. I think if you have understood this well, we can go further and look into the MATLAB code. Before getting into the MATLAB code, uh, uh, along with the Okumura model, we have also in this particular lab, we have asked you to find out what will be the median power. Okay, what would be the median received power? So for which the formula is PRD is equal to EIRP dBm. It should be in dBm minus L50 dB, which is the Okumura path loss, which you will be calculating, plus GR in dB again, where GR is the gain of your receiving antenna. Okay, so this also has to be calculated along with the Okumura path loss. We have included this as a part of your lab. So to find out the median power received, you will have to use this formula. That is, the medium power received in dB will be equal to EIRP in dBm minus L50, which is the Okumura path loss, which you will be calculating, plus GR, which is the gain of your receiving antenna. That also has to be in dB. Okay. And yeah, what is EIRP? EIRP is effective isotropic radiated power. Okay. It is given by PT into GT. Okay, so how, like, what does it represent? See, EIRP represents the maximum power radiated. Okay, maximum radiated power available from a transmitter in the direction of maximum antenna gain. So along the direction where your antenna has maximum gain, what will be the maximum power that is transmitted? That factor is what is EIRP. Okay. So using EIRP, you will be able to find, you already have L50. If you are being given with the gain of your receiving antenna, we will be able to find what will be the power received. Okay. Median power received. So I think, and then one more thing, we will have to, the data, when we have been given with the data, mostly EIRP will be given in dB. So to convert it into dBm, you will have to use, you will have to divide the value of EIRP by 1 milliwatt, and you have to take 10 log, to convert it to dB. That is what we'll be doing. So hoping you have understood this, we'll just go into the code. Just briefly, I will uh, take you through the code. So from here, if you see, you're taking the inputs. So here you're taking the input of your antenna, receiver antenna height, and we have exclusively mentioned that the range has to be between 3 meter to 10 meters. Okay. And similarly, we are taking an input from the user, which is for the base station, distance between the base station and the receiver antenna. Again, the range has been mentioned, it has to be between 1 kilometer and 100 kilometer. And then the third is the frequency, the frequency of operation, which will be, again, we have told it's between 150 to 1920 megahertz. As I told you, to calculate the received power, we would require EIRP. So we are taking an input, we are requesting an input of EIRP value, and GR, which is again required for calculating PRD. We will require the user to give us the value for the antenna gain. And in the formula, we found out that we are using to find out the median gain, the received power, we will be using the value for GR and dB. So the first step is to convert the value of your receiver antenna gain in dB. So we'll just use 10 log to the base 10, this is actually base 10, okay, into the value which has been given, GR. Now, as I told you earlier, we are not using value of EIRP directly. We are converting it into dBm. So to convert it to dBm, we are taking log 10 log base 10 EIRP divided by, it is divided by 1 milliwatt. So it is 10 to the power of minus 3. Okay. So this will help us to convert the value of EIRP in dB to dBm. And going further, the first step, as you know, in the formula is to calculate the value for your free space loss, for which you should know the value for lambda. So to calculate value of lambda, you're defining the speed of light, and then you know what is the frequency. The frequency which will be given to you will be in terms of megahertz. So what will we have to do while calculating lambda is C divided by F into 10 to the power of 6, because the frequency entered by the user will be in megahertz. Okay, so they would be giving some 1000 megahertz, so it should be 1000 into 10 to the power of 6. So this has to be considered separately, something which we need to pay attention to. And then we have all the credentials required to calculate your free space loss. So I'm sorry. Yes, we have all the credentials that is required to calculate the free space loss. So we know the value for lambda, we know the value for d, and we can now easily calculate the value of your free space loss. Now, the value for AMU and G area, the user has to find out for a given frequency. For a frequency of 900 megahertz and 30 kilometer distance between the receiver and transmitting antenna, you have found out AMU is equal to 43. Similarly, G area for 900 megahertz for a suburban condition, it is found to be 9 dB. So these two, the user has to find relative to what frequency and distance is being provided, and that has to be given in the program. And next is to find what will be the value for GHTE, which is given straight away using the formula 20 log H, 20 log to the base 10 HTE by 200. And to find out what will be the value for GHRE, we had seen there are two criterions. One is what happens if H is less than 3, and what happens if HRE is greater than 3 but less than 10. So if it is less than If it is greater than 3, then we will be using the formula 20 log to the base 10 HRE by 3. Or if it is less than 3, then we will be using the second formula. It is 10 into 10 log to the base 10 HRE by 3. So here now we have found out all the requisites to find what is the Okumura path loss. Okay, the path loss using the Okumura model. So we have the value of LF, right? We got the value for LF. We found out the value for AMU using the curve. The user has given us data using what frequency and the distance of separation. He found out it to be 43. Similarly, we found out the value for GHT. We found out the value for GHRE, and G area was similarly given by the user. So all the data that is required for calculating the path loss using the Okumura model is known to us. So using this relation, we can compute the value. So now we have computed the value for the propagation loss using Okumura model. Next step, we will calculate what will be the received power, the median received power, for which we had seen earlier the formula would be EIRP in dBm minus your path loss obtained using the Okumura model minus, plus the gain factor for your receiving antenna, it should be in dB. So we had already converted into dB, so that value has to be used. So with this, we have calculated the value for your Okumura path loss, means the path loss using the Okumura model. We calculate the received power, and now it's all about displaying all the results that you have used, that you have got, and then you can also have a graph which will be between your transmitter antenna height and your propagation path loss. Okay, so just to give an insight into how your input and your output will be, you will have to enter your receiver antenna height, you will have to enter your distance. Here it is shown wrongly, it is not 5000, it has to be in kilometer, it has to be 50 kilometer, it should not be like 50,000. It is in meters here, but it should be given in kilometers. And the frequency is 900 megahertz, and EIRP is given in, it's given as 1000. And here you can see the antenna gain is given as 1, and we get this as the corresponding outputs. Okay, and similarly you get an output graph which, as told earlier, it is a graph between your transmitter antenna height and the propagation path loss. So what you get to see is, as your your transmitter antenna height increases, your path loss will reduce. Okay, so I think with this we'll end this lab slot, and we will meet with the next lab in the next session. Thank you all.